All right, students, so today we're going to be doing the law of cosines. Sorry I'm not there today, but I thought I'd let you know that we have a special guest making today's video. I'll let him introduce himself.
Thank you, Mr. Flynn. It is a pleasure to be here. Pre-calculus students, I met your teacher 8 years ago at the White House where we were honoring the great math and science teachers from our 50 states. Just Google Presidential Awards for Excellence in Mathematics and Science Teaching for the year 2013. From the moment I met Mr. Flynn, I knew I wanted to see him teach math. So this is a dream come true for me.
Gosh, Mr. Obama, you're going to make me blush. Well, what we're going to do today is the law of cosines, and the law of cosines is this formula here. Now, it looks a lot like the Pythagorean theorem, and that's how you should think about it. So whenever I do law of cosines, I draw something that is looking right triangle-ish. So in other words, this is angle C and this is side C. So I'm kind of pretending for this angle here to be the right angle, though it's not a right angle, because if it was, we would just do Pythagorean theorem. I'm going to kind of pretend it is. So that means like this is little a and this is little b. So this is big B and this is big A there. And so we're doing this Pythagorean theorem, right? C squared equals a squared plus b squared, right? So c squared equals a squared plus b squared. And then since it's not a right angle, what we're going to do is we're going to subtract 2ab cosine of c. Now this ab, notice that's the two sides that formulate the, quote, legs of this right triangle. And it's cosine of c. If that angle C were, say, 90, I think we'd all agree that the cosine of 90 is 0, and that would make all this drop off. So really, this is kind of like the general form of a Pythagorean theorem, though obviously we don't bring it up this way because we deal with just 90-degree angles, but this is really a general form of it. So try to think about it like in these terms. Okay, so we're going to draw things that are definitely not to scale, but we're going to try to kind of help ourselves out to see what's going on with this. Okay, so, oh, by the way, if you don't have the formula down, pause the video now and write it down so you have it. Okay, so we're doing two questions today. The first one is this, and I'm going to go ahead and draw something that's kind of like a right triangle, right? And I'm going to, that angle is 111 degrees. That's angle C. Side A is 27. I'm going to call this side A. So this must be capital A. Side B is 18. So I'm going to call that capital B, and this will be lowercase c. So I'm going to do, again, Pythagorean theorem. Here are the two sides that are next to our, quote, angle, right? Our right triangle, so to speak. And so I'm just going to write out Pythagorean theorem. C squared equals a squared plus b squared minus 2 times those two sides again, 27 and 18, and then cosine of 111 degrees. So again, this is Pythagorean theorem basically, right? C squared equals a squared plus b squared. And again, the a squared and b squared are the two sides that are next to that angle. So if I work all this out, I will get C equaling, 37.43 degrees. Now, once we have that angle C, that is 37.43, we also need to get angle A. And what I can do now is I can do law of sines, right? I can mix these things up a bit. I notice I've got an angle and now the side opposite it to do law of sines. And so the law of sines says that the sine of 111 over, and we're saying that side opposite that is a 37.43. I'm going to say this is about equal to, because we did do a lot of rounding on it. It's about equal to the sine of angle A over the sine over 27. Okay, if I solve for sine of A, sine of A, it's approximately equal to 27 times the sine of 111 all over 37.43. We do the inverse sine on our calculator, making sure we have radians, and we will say A is about equal to 42.3 degrees, and we've got the two pieces. Okay, so we'll be using like both of these formulas here, but again, take your time on it, right? Draw things that look like a right triangle first, put the pieces in. Oh, Mr. Obama's got something he wants to add.
So you draw something that looks like a right triangle to help with the formula? Very clever.
Yeah, it is pretty clever, Mr. Obama, to do it that way. It helps us organize the formulas so we can see what it is that we're actually doing, because really, we're just doing the Pythagorean theorem with a little bit of extra. Now, once we find these missing pieces, we can do law of sines if we want to, because definitely that's a lot easier than law of cosines. Okay, one other question for us to do, and then I'll give you the rest of the time to kind of work on your assignment. And it's this one. So again, I'm going to draw something that kind of looks like a right triangle, though it is not a right triangle. It's just going to help me organize things a bit. Let's see, C is 7, so I'm going to call that side 7. So this will be angle C. Here's B is 8, so I'm going to put that here. And I'm going to call this angle here B. I know I've been calling it A, but it doesn't really matter. What's important is just label these so you understand what's going on. Make sure you reference what you're doing here. A is a 5. That's angle 5. And all they want us to do is find out what angle C is. So again, I'm going to think back that, this is a Pythagorean theorem-ish triangle. Here's the two sides that are adjacent to this hypotenuse quite set up. And so I can do Pythagorean theorem, right? 7 squared would equal 8 squared plus 5 squared. And we know that's not true, right? Because those do not add up correctly. But we have to do law of cosines, right? We're going to subtract 2 times these two sides that are next to the angle we're trying to use. So 2 times 8 times 5. And then the cosine of angle C, which we do not know, right? So if we work out the math on this, it's 64 plus 25. So we have 49 equals, let's see, what is that? 89. Solve for cosine of angle C. Which gives me 49. Well, actually, I think this thing reduces here to be 40 over, let's see if I subtract 89, it's a 4. Sorry, Mr. Obama's got me all confused here. I think that would be 40 over 80. And if we do the inverse cosine on this, we will get C equaling 60 degrees. And that's what we were asked to find. So these are the ways it works. To kind of recap a little bit, again, if we're doing something and we've got, say, an angle here, like we know this angle's 10 degrees, and we know this side opposite is 15, well, we should be thinking law of sines. However, let's say this angle's 10 degrees, and let's like say this side is 15 and this is 19. Notice here we do not have any angle on the side opposite it. This would indicate law of cosines. Okay. Well, looks like Mr. Obama's got one more thing he wants to add to us here.
Oh, so the law of sines is used when you have an angle and the side opposite of it. Kind of looking for a pair. Very nice.
Yeah, that's exactly right. That's how you know law of sines happens. Now, let me give you a hidden law of sines and see if this helps a little bit. Let's say I gave you a triangle like this, and I'm saying this is 10. This is 5. And this side up here, I'm sorry, this angle down here is like 35. Well, this is really a law of sines hidden in there, isn't it? Because don't all the angles have to add up to be 180? So if I subtract the two pieces there, let's see, what's that, 45? So 180 minus 45 is 135. So we can get this angle here to be 135. And now I'm like, hey, that's going to be a law of sines question, because it's like Mr. Obama said, we've got an angle and a side opposite it. All right. Well, hey, you're doing great. Sorry I'm gone this week. I'm down in the flex doing Kansas math assessment stuff, but I'm hearing good things about the work you're doing, so keep it up, please. Can't seem to stop this.